Welcome to Calculus 1 in Bethel here in fall of 2019, and to future online students. I'm talking to you as well. Today, lecture 1 is going to be the big picture of calculus. We're going to see the big ideas, what is calculus all about, in the context of both applications and some visual, physical animations that help us understand the subject better, I hope, in the long run. A lot of this content I'm going to write about at my blog. Some of you know about my blog, but not everybody. If you Google infinity is really big, my blog is actually the first one that comes up there. I will be posting relatively short blog posts about these lectures that give you summaries of these lectures and also things to make sure you know. Right now it's got stuff about linear algebra on there if you're interested in ever in linear algebra, but mostly what I'm doing for the fall here is calculus. So we'll do relatively short blog posts related to these lectures. What is today going to be about? Today is going to be about, again, trying to see the big picture. And while this is Bethel University, it's a Christian university, we also want to try to glorify God with what we are seeing and trying to understand. I would say the purpose of calculus is not only to learn things that are useful for you, but also to glorify God. To praise God for the beauty, I might say, that we see, but also the applications. And those applications start with an ancient mystery. What is that mystery? Does anybody know what the word planet means? If you do, say it loud. Anybody know what the word planet means? It's got a literal meaning other than just an actual planet in space. The word itself has a literal meaning. Does anybody know? No? Okay. It means wanderer. Why would it mean wanderer? Does anybody know why it means wanderer? Or have a guess? Any astronomy buffs? Nobody? Well, it's because when you observe the planets in the sky, they do seem to wander. Right? The background stars, you think about the Big Dipper, you think about Orion, they stay relatively fixed relative to each other. I mean, they move from night to night and during the night, but they stay relatively fixed compared to each other. But the planets wander around. Now, you're not going to see it in any given hour that you're observing the planet, but over night by night, they will move across the sky compared to the background stars, and sometimes they even go backwards. So this is supposed to be the Earth and Mars. Now, this animation goes back and forth. That doesn't really happen in real life, right? They don't go back and forth like that. It's just rewinding to the start here. There's the sun in the middle, and that's supposed to be Mars from the viewpoint of Earth. And it's a little hard to completely understand this, but basically, based on the fact that Earth travels around the sun faster than Mars, and Mars is further away, Mars appears to go back and forth across the sky. That's really weird, okay, right? If you didn't know that, that's something you can go out and learn about. The planets do seem to wander back and forth across the sky, and it's related to the fact that the sun is at the center, Mars is further from the sun than the Earth is, and the Earth moves faster around the sun than Mars does. How do you resolve that mystery? Well, one is the heliocentric model, the fact that the sun is at the center of the solar system. Copernicus came up with that model, though I think other people thought of it as well. And then there were a couple of people, Brahe and Kepler, who came up with, well, Brahe did a bunch of observations of positions of the planets over time, and Kepler came up with something called Kepler's laws that described this motion and helped them understand it better. Okay? For one thing Kepler did is that he helped us understand why planets that are closer to the sun move faster than planets that are further away. Okay? That's one thing that Kepler did. But Kepler's laws were very, what you might call empirical. They were just based on data, not really understanding things. And so it was Newton who came along, and Newton with his calculus, that helped explain Kepler's laws. What do I mean by Newton's laws? I mean, well, his second law, have you ever heard of that? F equals ma. People must have heard of that, right? Yeah, okay, I'm seeing some people now. All right, good. F equals ma is one of those laws. There's also a law called the law of universal gravitation. It's sometimes described as saying Newton was sitting under a tree one day and an apple fell down, and he came up with the idea of gravity. Well, no, that's not quite right. People thought of gravity before Newton right? They knew apples fell down. But what Newton realized was that the force that caused the apple to fall down is the same force, he said in his writing, that caused the moon to go around the Earth and then ultimately the Earth to go around the sun. Okay, that's universal gravitation. Everything that has mass attracts everything else. Okay, you're sitting next to your neighbor, you have a gravitational force between each other. Okay, it's very, very weak, but it's there. It can be measured actually. All right, so that's historically what motivated calculus. Newton and Leibniz, people say, are the discoverers of calculus. From that video by Steven Strogatz, he said he disagreed with saying Newton and Leibniz started calculus. Did anybody remember who he said started calculus? Way back a couple thousand years ago. Archimedes, yeah. Archimedes was the true founder of calculus, though he did not have our notation. Okay, he didn't have our algebra notation to describe calculus in the ways that we do today. What is calculus? Well, in a short sentence, you could say it's the mathematics of modeling change. If you want to get a little bit more specific, you can say functions, limits, derivatives, integrals, and infinite series. Again, with a Calculus 1 class, some of you have had calculus, some of you have not. Those who've had calculus, maybe remember those words. Okay, we want to study those things and understand them. Again, a highly recommended book, this one, Infinite Powers, How Calculus Reveals the Secrets of the Universe by Steven Strogatz. I highly, highly recommend this, not just watching his video, but actually reading his book. There it is. Okay? You want to understand the big picture of calculus. Here are some applications highlighted in Infinite Powers, some of which were in his video, The Beauty of Calculus. Computer animation and facial surgery. You may remember that from the video. You need to do some facial surgery to somebody. It's hard to know how their face is going to deform after the surgery, if you need to move some bones around or whatever. Calculus can be used to model that and predict what they're going to look like. Okay? And they can look at and see what they're going to look like before you do the surgery, and they can be happy about it or not happy about it. And if they're not happy about it, then maybe you try to make some adjustments. Newton's laws of motion, like I just mentioned, for the planets, including applications to planetary motion, which is important certainly for getting spacecrafts to Mars and things like that. And GPS. GPS, you need to know Newton's laws as well as Einstein's laws, relativity, to be able to make sure your GPS is accurate. Image compression is another application mentioned in the book, not in that video, I don't think. For efficient data storage and retrieval, for example, fingerprint databases. Analyzing performance in sports was hinted at a little bit in the video. Understanding and combating infectious diseases. Okay? We have a lot of exposure to diseases these days because of our interconnected world, right? We can all get in an airline and be in Australia within 12 hours or something. That's pretty amazing when you think about it, okay? Only in the last 50 years or so have we developed that. That means we're more susceptible, though, to infectious diseases. So we need to model the spread of infectious diseases so we can try to stop those diseases before they infect a lot of people. Aerodynamics of flight. Okay, you can be happy that they use calculus to study aerodynamics of flight. Otherwise, your plane might fall into the sky, or be more likely to at least. And discovery, like I mentioned last week in the intro, of electromagnetic radiation, leading to many commercial applications: radio, TV, microwaves, and cell phones, etc. Okay, so calculus, while not the only thing in helping people discover these things and get these applications, is certainly a very important player. What are the main applications that we're going to study in this course? Motion, okay? Why? Why motion? Well, one thing is something we're all pretty familiar with, right? We're all familiar with walking, running. Okay, I'm not going to run. I'd probably trip and fall, okay? Jumping, throwing a ball, rockets moving through the air, airplanes, spaceships. Something we're all fairly familiar with, and it also sort of serves as a way of thinking about other applications as well, because it's so visual. Okay? Technically speaking, we'll be talking about something called kinematics, the relationship between distance traveled, speed, and acceleration, and also between position, velocity, and acceleration. Technically speaking, speed and velocity are different than each other. Sometimes people use those words interchangeably, but they really are different. Speed is really the absolute value of velocity. Velocities can be positive or negative depending on what direction you travel. That's called kinematics. We will talk a little bit about dynamics, which is trying to understand the kinematics with forces in Newton's second law, especially with regard to like dropping something. That's called free fall under the influence of gravity. With or without friction. What I mean by friction is air resistance. And then there's something called simple harmonic motion, which is basically just back and forth motion, like a mass in a spring or something, okay? Which comes up in a lot of situations. With or without external force. Flows, what does that mean? That means like fluids flowing, pollution, traffic. Now we'll be thinking about these at a real basic level. You can get real detailed about how fluids flow, and it becomes super duper complicated if you do. We're going to be real basic, like how fast is the water coming into the tank or something like that. 5 gallons per minute, 10 liters per hour, okay? It's coming in at a constant rate, for example, is one thing that we'll be thinking about. Keep it simple. Same thing with pollution, okay? Pollution is really, you know, if you're thinking of it in terms of a gas or something like that, that's fluid flow as well. That's real complicated. Keep it simple. Traffic can get complicated, but we can keep it simple. How many cars are going through the intersection every minute on average or something like that is a way to keep it simple. Exponential and logistic growth and exponential decay. This is essentially population growth, and usually the application here is like radioactive decay, which I say there. Finance, compound interest, present value, future value. These words, by the way, apply to other situations besides just putting money in the bank. Something called annuities, which are just a series of payments, like payments on a loan that you are borrowing money for a car or something, you need to pay it back every month. And something called bonds, which is a little bit more complicated. And we'll look at applications to probability and statistics, which is the foundations of what's called data science. We have a math and data science major here at Bethel. If you're interested in that, that's something you could consider. Knowing probability and statistics is important for that. Essentially, in this class, we'll just be doing some data modeling. And I think we'll talk about that in context to see what it means. Though if you've ever heard of a normal curve, a bell-shaped curve, that's basic data model. I claim that almost all the content of calculus, this is a big claim, is related to just one key equation. How can that be possible? And what equation would that be? This is the secret of the universe. Much of calculus consists of generalizations and extensions that do get complicated of just one key equation. What key equation am I thinking of? Something you might have learned in 8th grade. Distance equals rate times time. And I'm writing it both with a cross and a dot. I'm usually going to write it with a dot, but just if you like the time symbol, put it there once at least. Oftentimes when the variables are words, we'll use a cross for the time symbol. Distance equals rate times time. You're walking, okay, I'll walk a little bit slowly here so you can follow me just slowly. Walking at a certain rate, constant rate, oh, I don't know, 1 meter per second or something here, for 6 seconds. How far did I go? 1 meter per second times 6 seconds is 6 meters. I probably went farther than that, but you get the idea. This equation's got a relative. Divide both sides by time. Rate equals distance divided by time, or rate is a fraction distance over time. This equation, you can think of the rate as giving you the exact constant rate. How fast are you going? If you are going at a constant rate. If you're not going at a constant rate, if you're speeding up and slowing down, and speeding up and slowing down, and even going backwards a little bit before going back the other way, it's still useful, but it doesn't give you a constant rate. It gives you an average rate. In that case, what's your average speed or velocity? Here's a visual. Motion at a constant rate. These three cars are each traveling at a constant rate, different constant rates. Green one obviously going the fastest, the red the slowest. I'm going to say these three cars are moving at rates 1, 2, and 3. 1, 2, and 3. Look at the time goes up to close to 10 seconds. Actually, in my code, it really was going to 10 seconds. It's just that this animation is not going all the way to 10 seconds. Rates 1, 2, and 3. That doesn't have much meaning, though, unless you have units. That's a real important thing to realize for this class. You need to have units on numbers if they're going to have to be related to an application. Now, if they're not related to an application, if it's just pure math, then you don't need units. Though it's often helpful to think of units. That can be a helpful thing. So what are examples of units for something like this? That can be pretty much anything you can think of here. Meters per second, feet per second, miles per hour, though if they were miles per hour, 10 hours would go by, and this is only 30 miles, so that would be very slow. Okay, there's lots of different units that could be used, but if you're talking about a specific application, you have to give specific units. Here's two of the cars and two graphs related to these two cars. The red and the blue, the slower two. The red horizontal line here is the speed of the red car as a function of time. It's constant, 1. The blue horizontal line is a graph of the speed of the blue car versus time. It's constant, 2. It's not changing. Constant speed. What are possible units of the speed? We already mentioned those, like meters per second. Let's go ahead and just pretend it's meters per second. The distance traveled, you can see as graph as well, but not in the usual way. And I'm saying distance equals area? How can that be the case? How can a distance be an area? What am I doing?
Because it's rate multiplied by time.
Yeah, it's because it's how the units for rate times time work out. If you think of, say, 2 meters per second times 10 seconds, the seconds cancel, giving you 20 meters for the units, which is a distance traveled. And you can, with this second blue graph here, over the time interval from 0 to 10, think of that as the area of this rectangle. Because its base is 10 and its height is 2. So in that sense, you can think of it as the distance traveled is that area. That's a really important perspective in calculus. The area under a graph, when the graph is a rate, meters per second, for example, gives you the total amount accumulated. In this case, the total amount of distance, 2 meters, or 20 meters, excuse me. Okay? So it's not that the distance is literally the area that you see. It's just a nice way to imagine it. When you find the area, you multiply the units on the axis. The units on this axis is seconds, the units on this axis is meters per second. Multiply those two units, the seconds cancel, leaving you with an area in meters. Again, not literal, it's just in your imagination, but it's a useful thing in your imagination. Could you graph the distance traveled for both cars in an ordinary graph? Say in the same set of axes. Sure. What would the graphs look like? What do the graphs of t and 2t look like? Pretty simple.
Rectangles?
Well, that's where they come from here, but I'm talking about an ordinary graph that's either like a parabola or a line or straight lines, yeah. maybe something like that. This is, say, y equals t. If this is a y-axis here, that's a t-axis. This is y equals 2t. Straight lines, because these are linear functions, constant slope. This one has a slope of 1. This is 1 times t. This one has a slope of 2. They go to the origin. The graph goes to the origin, because at time 0, they haven't traveled any distance. There's no area yet under the graphs at time 0. If the slope of the first one is 1, what's that value of y right there? The scales on these axes are not the same. 10. Yeah, I heard somebody say it. Right, when t is 10, then y is 10. With this one, when t is 10, y is 20. So this one goes up to 20. Okay? These functions, these graphs, are keeping track of the total area that's accumulated as t continues to increase for these graphs. Their slopes equal the values of these functions, the speeds. The speed is the slope of the distance traveled. It's also called derivative. There's another situation, fluid flow. Got some colored water here, right? Some dye, some paint, whatever you want to think of it as. Coming out of some faucets into some tanks, some vats. The 3 vats are filling at rates 1, 2, and 3. Well, again, we need to get units if that's going to make any sense. The units would depend on how big the vat actually was, by the way, and how fast the water was actually coming in. But just for the sake of pretending, say the volume is in liters, and time is in seconds. Then we could say this one, the red one, is coming in at what? What would the units be? Go ahead and say it. Liters per second, right? The blue one, 2 liters per second. The green one, 3 liters per second. The blue and green are coming in faster than the red. So the volume is getting higher faster. We're going to again look at 2 of these. The flow rate, these graphs are flow rates now, not speeds. But they're analogous to speeds. They're measuring how fast something is happening. How fast is the colored water coming in? Those are flow rates. 1 meter per second, that's the constant value of this red graph. 2 liters per second, that's the constant value of this blue graph. The total volume is graphed too, but not in the usual way. How can the volume equal an area? Volume equals area? Once again, same theme. It's not that the area is literally a volume. It's just the way to conceptualize it. So with the blue one there, the flow is coming in, the water's coming in at 2 liters per second. For 10 seconds, the final answer is, well, 20 still liters. Instead of meters per second, this is liters per second. The area still has units that are the product of these things. Liters per second times second is liters. And once again, we can graph these in the usual way. I probably shouldn't have erased my graph. T and volume up here. Let's call it V equals T now. And V equals 2T. Once again, those are straight lines through the origin with a slope of 1 and a slope of 2. They're telling you the constant value of these functions. Right? These functions are the derivative of that function, of those 2 functions. Actually, I don't remember if I said that correctly the last time with the moving cars. These functions, the flow rates, are the rates of change, also called derivatives. of those two functions over there. I might have said it the opposite way, I don't remember. And again, it's a generalization of the distance equals rate times time equation. It's now volume equals rate times time instead of distance equals rate times time. One more application, population growth. Once again, we got a quantity that's growing over time. In this case, population. How many bacteria or something? Growing at rates 1, 2, and 3. And if these are really bacteria, probably the units for those would be something like, I don't know, billions of bacteria per minute. Does that sound reasonable for bacteria growth? I don't know. I should probably ask a biologist. Maybe just millions of bacteria per minute or per hour or something. Once again, the green one's growing 3 times faster than the red one. The blue one's twice as fast as the red. Once again, we can look at, say, 2 of them. Now the area is a population instead of a volume. The growth rate in both cases, the derivatives, are graphed, and they're constant functions, horizontal lines. What are the units for the growth rate? We already mentioned, let's say millions of bacteria per hour. Seems most realistic. The total population, again, is graphed, but not in the usual way. We're seeing the areas instead of an actual graph like this. If I were to do the same kind of calculations, I'd do, say, 2 million bacteria per hour times 10 hours gives me 20 million bacteria. Really, I should probably write the word bacteria, but I'm just trying to save a little time here. As an area with units here, you multiply the units, the hours cancel, and it doesn't matter, by the way, if it's plural. Plural still cancels with singular in this scheme. Okay, to give you 20 million as the area, the population can be represented as an area. And over here, the population can be represented with an ordinary graph, like that. T equals T, T equals 2T. Once again, these things are derivatives, rates of change of these graphs. Those graphs have constant slopes, 1 and 2. Just like these values are constant at 1 and 2. Yes, we could graph the total population in most situations on the same set of axes. One more animation like this before we're going to go on to something else. It's like, what if the rate is changing? This is where the true calculus comes in, right? That's other stuff is really not calculus. It's not hard enough to be calculus, you might say. Steven Strogatz said that calculus wants to make hard problems easier, but those problems are too easy. Calculus develops tools to try to make hard problems easier, doable, at least not that it's easy, it's just more doable. What if the rate is changing? Look at that. Try not to get too dizzy as you watch. Now I've got 3 cars, and they're not moving at a constant rate. They speed up, slow down, all 3 of them. They still travel the same amount of distance in the same amount of time. What can we say about the speed and distance traveled in this situation? The speed is not constant. Its graph is not going to be a horizontal line. The distance traveled is not a linear function of t. It's not going to be a straight line. Though it will go up, it'll still be an increasing function. There's the speed for the red and the blue cars. You can see it's not horizontal lines. It's going up and down. It's like a sinusoidal wave, you might say. When the graph is high, it's going faster. When the graph is low, it's going slower. A little hard to tell, maybe. When the graph is high in value, the car is going faster. When it's low, the car is going slow. Is the distance traveled still the area? Is the area still equal to t and 2t? The distance traveled is still the area under the graph, but the areas are not equal to t and 2. What kind of graphs would you get if you tried to graph the distance traveled? I already sort of hinted at it with my hands. Still increasing, but do you think you could describe it in some other way? It's not straight. Does it go up and down like those?
No.
No, what do you think it does?
I think it goes straight, and then it goes to the right, and straight.
So you're proposing something like this? Okay, I think that's a good guess. I'm meaning for the distance traveled to be a little smoother than that, because these graphs are smooth. They're not just low, high, low, high, low, high. And because of that, it's going to just round out those corners. But otherwise, you got the right idea. So probably something more like this. And maybe, okay, no, the speed doesn't actually ever equal 0. So the slope is always going to be positive. Something like this. By the time you reach 10 seconds, or yeah, 10 seconds, say. This is the distance traveled, say in meters. Something like that is going to be the graph of the distance traveled as a function of time. Say we look at the blue graph. The blue graph here is the derivative, the rate of change of this graph. It's giving you the slopes of this graph. Here the slope is high. Here it's relatively low, just a slight positive slope. Here it gets high again. Here it gets low again. High again, low again. It's oscillating in the slope just like the value, the output of this is oscillating up and down. But this one's got to keep going up because the car still does keep moving forward. It can't be looking like this, though it's related to that. Again, we say this is the derivative of that. We also say that is the integral or antiderivative of this. All right, we're going to move on to something slightly different here, though related. If we're going to be able to get to the point where we can be more precise about what we're doing there, we need to deal with the details of calculus, limits, and derivatives. And we need to use something called the infinity principle. This is Steven Strogatz's term for this principle that you see here. To shed light on any continuous shape, object, motion, process, or phenomenon, no matter how wild or complicated it may appear, reimagine it as an infinite series of simpler parts. Analyze those and then add the results back together to make sense of the original whole. So the complicated thing in that last slide was the motion of the car that's fast and slow, and fast and slow, and fast and slow, and fast and slow. We'd like to know the total distance traveled for that. If somehow we could measure the velocity at every moment, fast and slow, and fast and slow, fast and slow, fast and slow, fast and slow, maybe we could figure out the distance traveled. Now that might seem a little silly because obviously the easiest way to figure out distance traveled is to say, hey, where'd you start? Hey, where'd you end? What's that distance? That's the easiest way to figure out distance traveled. But we want to understand the relationship because that does have other applications where it's maybe not so easy to figure out distance traveled, like a spaceship going to the moon by first going around the Earth and going along some curve, okay? It might be easier to keep track of the speed or the velocity in general more easily than to keep track of the distance traveled in that situation. There's something called Zeno's paradox that was thought of a couple thousand years ago that's related to the infinity principle. Zeno's paradox is this, well, like it's stated in a number of forms, but the way I'm going to show you is there's Achilles and the hare, the rabbit. They're in a race. No, I got that wrong. Achilles is the hare. Achilles and the tortoise in a race. Now, obviously, Achilles, like a hare, a rabbit, is faster than the tortoise. So Achilles gives the tortoise a head start. Zeno's paradox says that the tortoise wins the race anyway, because Achilles can never pass the tortoise, even though Achilles runs faster. How can we say? What? How can that be? Can we visualize this way? So there's Achilles, there's the tortoise. Achilles starts at spot 0, the tortoise starts at close to 10, which is, I guess, the end of the race. If Achilles is going to catch up to the tortoise, he first has to go half the distance between them, so to speak, or cover half the, so the tortoise during a certain amount of time goes a certain distance. Achilles, during that same amount of time, has to cover a certain amount of distance that is not how far the tortoise went. I'm not saying this very well. Think of it this way. Think of it as in terms of half. I don't know that this is the animation that actually does it in terms of half. Yeah, that's what I'm doing. 0 is the start for Achilles, 10 is the end. During a certain amount of time that it takes Achilles to go from 0 to 5, the tortoise is going to go a little bit further. And then there's a certain amount of time for Achilles to go half the remaining distance from 5 to 7.5, which is right about here, the second step. But wait a minute, the tortoise has still gone a little further. Then there's a certain amount of time for Achilles to go half the remaining step to 10 as well, from 7.5 to 8.75. But wait a minute, during that time, the tortoise has still gone further ahead. How is Achilles ever going to pass the tortoise? Because at each step, when Achilles covers half the remaining distance, this tortoise has still gone a little further. Now we know, obviously, in real life, Achilles will pass the tortoise. Maybe not until time they reach the finish line, but he will pass the tortoise. So what we really have here, if you want to try to resolve this paradox, in a sense is an application of the infinity principle. This quote-unquote complicated idea of Achilles passing the tortoise can be broken down into little steps that you do infinitely often. It's almost like Achilles takes infinitely many steps of these half steps and does reach the tortoise at some point. There's like a completed infinity. Now, you can ask a philosophical question, does that really happen? Can you really have a completed infinity like that? And some physicists would tell you no, because they would say, at its heart, reality is discrete, not continuous. But as far as we're concerned, and as far as we're concerned modeling with calculus, we can pretend that Achilles takes infinitely many steps and does reach the tortoise once they get to the 10. And here's a more typical way to visualize it. Over time instead of over half steps toward the location 10. Achilles does reach where the tortoise is here at location 10 at a certain moment in time, and then passes the tortoise. But this is an ancient paradox that calculus can be thought of as resolving. How about the area of a circle? Why is it pi r squared? Because my teacher told me. Yeah, but how did your teacher know? Because their teacher told me. It's like an infinite sequence backwards in time. Who was the first person to think of this? That the area is pi r squared. Well, a couple thousand years ago, people did know the area was proportional to the square of the radius. But they didn't know what the constant of proportionality was. And in fact, people didn't call it pi until somewhere, I'm guessing here, in the 14, 15, 1600s. They didn't actually call it pi, even though pi is a Greek letter. How'd they figure out the formula's pi r squared? How'd they figure out what pi was? That took calculus. The ancient Greeks knew the ratio of the circumference of a circle to the diameter stays constant as the circle changes size. So, no matter what circle you have, you take the circumference divided by the diameter of that circle, you're going to get this mysterious number we call pi. Surprisingly, the Greeks didn't call it pi, even though pi is a Greek letter. Maybe it's in honor of the Greeks. Actually, I'm lying a little bit here. Archimedes, you might say, did know a little bit about pi. He didn't call it pi, but he did know it was a special number, and he did try to approximate it. Once the ratios from the last slide are proved to be constant, which does have to be proved, they define the number pi. So the formula for the circumference is true by definition. Take c over d, it equals pi. Solve that equation for c. Multiply both sides by the diameter, d. It's true by definition once you prove that that ratio is always the same no matter what the circle is. So there's nothing to prove there. C equals pi times d, which is the same as 2 pi times the radius. But why should pi show up in the formula for the area of the circle? Pi should show up in the formula for area. Area is a fundamentally different kind of thing than length. And they're related, obviously, but the key to a visual proof of this you saw in Steven Strogatz's video, The Beauty of Calculus, and I'm going to show you here, is you can slice up a circle into many, many pieces of pi and then rearrange them to look like a rectangle. See what I'm doing there? Slicing up that circle in many, many pieces. 14 pieces, then it gets higher to 32 pieces, then I rearrange them to look like a rectangle. That rectangle has base c over 2, circumference of the circle over 2, and height r. Think about that. Think about the height. Focus on that radius. Watch those get rearranged. Yeah, those lengths is the radius because they're the lengths of these pieces of pi there. And the bottom of it is half the circumference because you got half the circumference on the top and half on the bottom. So it's c over 2. So the area of the circle is the same as the area of the rectangle. Base times height, c over 2 times r, which is pi r squared because the circumference is 2 pi r. Replace c with 2 pi r, cancel the 2's. But wait a minute. This picture right now is not exactly a rectangle, right? It's only approximately a rectangle. This is an application of the infinity principle. We're imagining if we take this slicing out to infinity, if we didn't just do 32 pieces, but a million or a trillion or a Google, and then did the rearranging, we essentially would get a rectangle in the limit as the number of slices goes to infinity. So therefore we would say the area of the circle does equal the area of that rectangle. That's not a proof, okay? It's not a rigorous mathematical proof because it's hand-wavy, kind of vague, intuitive idea. But it does get at the heart of why the area of the circle is pi r squared. Here's another way you can think of it. This is based on a video off my favorite YouTube channel by 3 Blue 1 Brown. Actually, 3 Blue 1 Brown is the name of the YouTube channel. Grant Sanderson is the name of the person who runs that channel. And he's got a visual like this. Over here you got a circle. Instead of slicing the circle like pieces of pie, wedges of a pie, slice it with rings. Like you see right there. Slice it into a lot of rings, and then rearrange those rings, straighten them to be thin rectangles. Technically speaking, my animation may not be doing it perfectly in terms of always keeping the appropriate length correctly, but the final length is correct. The height of this skinny rectangle, say over here, right now, is the same as essentially the circumference of the outer ring. And if you do that, keeping those lengths constant, if you truly are doing that, then you've got an area that's essentially a triangle. And in the limit, when the number of slices goes to infinity, it is a triangle whose bases r and whose height is 2 pi r, the circumference of the entire circle. The area, therefore, is 1/2 base times height, 1/2 r times 2 pi r, which simplifies to pi r squared. Once again, it's not a rigorous proof. It's just a visual of the main idea that gets at the heart of what calculus is about. For any finite number of rings, it's really just an approximation. But the infinity principle says if you then take the limit, go out to infinity, repeat this slicing into rings process infinitely often, then this really becomes the area of the triangle. And this becomes exact. Okay? That is the big picture of calculus, and that is at the end of lecture 1. Okay? See you next time.